you recording the time span, okay, when the state remains unchanged, okay? It means you record the time period before or between the two change. This is another way to record, to describe the systems. So maybe just spend like 1 or 2 minutes to think, okay, by yourself is that which way, okay, just by yourself, okay, you think which way is better to describe the systems, okay, from your own perspective. For example, now if you just recall what you have done today, from the starting of the day, in the morning, until now, you think of what are the things you have gone through. Okay, if you want to describe what you have done, how do you want to describe it? Whether you want to describe the time span, or you want to describe the change?
State time span, both.
Both, yeah. For example, what have you done today?
First I corrected the code, then I corrected the document,
Yes.
and then I did the training,
Okay.
which I had to complete.
Okay, so you collected the...
So three
yeah.
state change.
Yes.
With,
No, the first one, what you said just now.
I corrected the code which I had written previously.
Okay, you
changed
corrected the code which you written previously, okay.
Because new thought came, so I thought let's try to implement that thing. And
Okay.
then, so time span is important to check out the productivity.
Yeah.
Then corrected the document.
Corrected the document.
Yeah.
Okay.
And then after that did the training.
Okay.
So and with
Okay.
time span.
Okay, yeah. So this is what I'm trying to say to you is from a human's perspective. Most of the time we actually look at the time span. When we want to describe something, we look at the time span. For example, just now I had lunch for a certain time so when we say I was having lunch, meaning that actually happens during certain time span, and at that time, during that period of time, I remain my state as in the lunch time, okay? So this is how the human describe discrete event systems. So that's why that if you want to look at most of the commercial software, okay, in the market, so they are actually following this the paradigm, okay, which is actually using the time span, or maybe we call activities, okay, they call this as activities. They use activities to describe a discrete event system. To say that, okay, they start with certain activity, after activity finish, they go to another activity, then followed by some other activities, okay, so this is how most of the case the discrete event simulation is described. So why I say this is if you want to look into like those software like Automo, Flexterm, like last week introduced, if you take a closer look, how you describe their model is mainly from the activity-based perspective. Even there's some like open source simulation software, okay, when they describe their systems, they're also using activity-based approach. For example, they also have a scheduling to say that sometimes schedule instead of an event, you actually schedule activities at certain time for certain duration. Okay, so this is some things you need to bear in mind. But okay, we should say that activity-based approach is easy to understand, okay, easy to communicate by humans. But the thing is, sometimes it might have certain limitations. Okay. For example, let's take this as an example. Let's say this. Okay, now we are having training. Okay, so after training, you need to go for a meeting, for example. Okay, you need to go for a meeting. Okay, after the training, probably for 1 hour, you need to go for a meeting. So if you come from the activity-based approach, that thing is easier. Just say, okay, 1 hour training followed by another hour, maybe the meeting. Okay. But if you want to ask what's happening between your, the training and the meeting, is it because the meeting was scheduled, okay, previously, yesterday, okay, so that you know after 1 hour, when the training finished, then you have another activities like a meeting you need to attend. This can be one scenario. Then the other case will be, our training is actually can last for 2 hours, for example. But in between, you receive a call from professor to say, okay, come for a meeting, we need you. Okay, this is another case. But the consequences you will see are the same. After 1 hour training, you go for a meeting. Okay, it can also be another reason. Okay, say that you think maybe training is boring, so you just want to go outside, then you met a professor, then you just take you into the meeting room. This can also be another case. Okay, so you can see that by just telling the time span for the activities does not tell you the full story. Okay, especially for those industrial systems. When a decision is going to be made, okay, then you need to know that what are actually the protocols when this transition happens. Okay, let's take just one of the industrial problem to describe the same situation I just mentioned. Is that you see the container moving in the port, right? It's carried by the prime mover, okay, or AGVs. Okay, so it takes some time traveling by the AGVs until it's reached at the bottom of the key crane. Okay, then the key crane start to hand over the container to lift it and load it to the vessel. Let's consider this scenario. We have two activities. One is the traveling, the other one is actually loading to the key crane operation, loading to the vessel. But what is happening in between? Okay, if you just use the activity-based approach, it might be difficult to describe what is really happened. But if you use other things like events, okay, meaning that you're actually talking about, okay, when the AGV arrives, okay, then you send certain information, then when they receive this information, although it can happen at the same time point, okay, then you actually describe the interactions, okay, between the two different parties, entities, or between the two different activities, okay, then we can see that where is actually the time point, where is actually the we call it event that a decision need to be made, and what are the information available at that point of time. So that is actually to say that if you want to do the analytics based on those decisions, then maybe the event-based is a better way to describe, okay, the situation, what is happening inside the systems. Okay. Then you may ask a question is, why you think that those software, okay, available in the market is able to describe industrial systems? Okay, I just said some of the limitation, but why it's still capable for those software to describe discrete event systems? Okay, so I might not be right, but here is my understanding is that because they assume there's a certain protocols, okay, happening between two activities. When the assumption is holds, okay, when assumption holds, then they can simply use activities, okay, to describe the system. But if the assumption is not valid anymore, okay, then we need to go back to the event-based approach. Let's take this as an example. Like we have this, I think yesterday Reza asked this question about the single queue. Okay, when we have a customer arrivals, we have a queue, then after we have a server. Okay, then if I ask this question is, for example, now this is arrival. For example, this is not a server. This is just some like outside the universe. Okay, we have some arrival patterns. Now here we have a queue. If you just consider this one, I mean some arrival comes, then there's a space, okay, for the customer to wait. Okay, if you just consider this kind of systems, what we'll have is we try to identify what is happening between the arrivals and queuing. Okay, so what are the transitions between these two? Somehow we can see that this is actually a simple case. It's just a one event, meaning once arrive, then it's in queue. Okay, so the event is clear, provided that the queue is actually unlimited. Whenever it's arrived, we know that it can be in queue. Okay, it can in queue. Okay, so this is the assumption. When a queue has infinite capacity, then it's like a single way, or maybe like one handshake. Okay, maybe a one handshake. Communications or transitions. Okay, so it's a single event here. But if you consider the case one, the downstream have capacity. For example, after the queue, you need to enter the server, but this server actually got certain capacities. Can we say that whenever it's a DQ from here, or whenever there's some customer arrive at the queue, it can be served immediately? No, right? So they need another way of communication, which is either to check whether the server got capacity, or is that to check the server need to go back to inform the queue that there's any vacancies, okay, for the servers. So in any case, there need to be a two-way communications between the queue and server, right? So this is what we refer as two-way communication, or like a two-way handshake.
Okay.
Okay.
So the queue can check whether the server is busy or whether the server will tell the queue we are open.
Yes,
Okay.
yes. So they need to be two-way. One for information, the other is actually the physical flow. So later, I mean, in detail, I'll talk about how to design, how to describe.
Which one is the best approach? The queue checking busy or the server telling the queue?
This probably later. Later, I will talk about this.
Okay.
Talk about this when we go to maybe a modularization.
Yeah.
I think this will be a later phase.
Okay.
Here is just want to try to persuade you that event-based is a better approach, and activity-based approach is working because there's some assumptions. Okay. This assumption is to say that here is actually the protocol. So if this is the protocol, then what you can have is whenever I put a queue, meaning that on the left-hand side is a one-way communication, on the right-hand side is two-way communications. Okay, we can say in this way. Whenever there's a server, we can see that the left-hand side is a two-way communication, the right-hand side is actually one-way communications. Okay, so this is assumption. When this assumption is there, then we can go to the activity cycle diagram. So I think in the last internal training, I introduced this activity cycle diagram to some of you, and we say that this is an approach used by the activity-based discrete event simulation modeling. Okay, but at that time, I actually mentioned to you that there's a certain rules we need to follow. Okay, is that this is one activity, this is one activities. Between the activities, there need to be some queue, which have infinite capacities. You may ask a question, so why is the case? Why the one activity cannot be followed by another activities, but they need to be certain queue, one queue inside? And why they cannot be two queue connected together? Okay. Then if you remember what I taught in the last slides, you will know the reason. Because from here to here is a one-way communication. From a queue to an activity or to a server is actually a two-way communication. So that's why if you think the events between them, okay, at the interface between the activities, then you know that how they can be connected together. Okay? So if you want to put it in a way that one activity follow another, okay, then what you need to do is you need to change a fundamental protocols, okay, for the queue and the activities. So that will be the reason, okay? Okay, so yes, so let me see how should I continue now? So yes, this is about the difference between the activity-based and event-based. And inside here, okay, in our group, because we need to focus on those decision making, okay, and because we want to model a system with a higher flexibilities, okay, so that's why event-based is a kernel we should follow, is a core we should follow. Meaning that every model, we should build it, we should control it, okay, at the event level, okay. But for simplicities, okay, we can actually wrap it and put it as a module. We can treat it as activities later, okay, to use this one to assemble for a larger system, no problem at all. But we need to control it. When we build it, we need to understand it at the event level, okay. So this is something I'm trying to explain to you. Another thing is okay. So these are the two formalism. The first one activity-based. The second one is actually the event-based. So actually, there's another formalism called a state-based. Okay. So I think because you have certain background knowledge, so I think it's better to elaborate to you now. Okay. Together. Okay. For this three formalism. So what does this state-based formalism mean? Okay. State-based formalism is actually to say that we focus on the state variable. So yesterday we said that state variable is used to track, okay, the system, to describe what we are interested, okay, in the observation, and actually a state is actually independent. State itself should not depend on activity. State itself should not depend on events, but rather it's the other way. Its events should be defined in a way that it change the value of the state. or activity should be defined in a way that the state variable remains unchanged during a period of time. Okay, so actually dependency is the other way. So if we just look at the state, okay, of the systems, so we can see that probably does have some way, we have some way to like divide the state, okay, into different areas. Okay, we can cut the state variable into a smaller piece, so that we can see that this smaller piece of state variable actually follow certain properties or follow certain, there is a certain behaviors, okay, which actually depends on this smaller group of the state variables. It's similar like the OOP, okay, object-oriented programming. Okay, so if you know object-oriented programming, if you don't know, I think you might be in trouble. So yeah, so you know the OOP. So the basic principle is you want to like encapsulate the properties together with the behavior. Okay, so I think the state-based actually follow the same way. Is you have a large systems and there's so many behaviors, okay, in these systems, so make you headache. Okay, then what you do is you actually cut the properties into a smaller group. The property means the state variables. Okay, you cut these state variables into a smaller group. Then you actually identify those behaviors strongly related to this behavior as to this state variable. You group them together. Okay, so this is actually what the state-based approach means. Okay, so if you still use this queue, a simple queue example as one example, you can see that here we can actually have a certain like state variables. We can put them into the different areas. For example, the arrivals. Okay, we can have state variables to describe or record how many customers have arrived. Okay, so this will become the properties of the, maybe we call the generator. This will be one set of the properties. Then we have another set of properties describe all the information about the queues. Okay, it can be how many people, how many customers are now within the queues. So this is about the queues. Then we can have another set of activities, state variables to see how many customers have been served, okay, in the server. So at least, although this is a very simple case, we only have like 2 or 3 state variables, but if we divided them into this way, we can see that we can actually identify certain events. We can actually identify certain events that is closely or strongly related to this state variable. For example, for the state, okay, for the state, for the arrival, the generators, okay, the state variable is how many have arrived. So what will change this value is whenever there's a new arrival, this value change, right? Then this arrive event, okay, this arrive event will become the event that strongly attached, okay, to this state variable. Then the second thing is, okay, for the queue, you can see that the enqueue and dequeue is actually the event which is strongly related to this number. And also for the server, start service and service, okay, will be the events attached to this value. So in that case, we can do a modularization. Okay, we can do a modularization. Or in some sense, we can see that how do we do the modularization in all this modeling is because of the state-based formalism. State-based formalism. Okay. Then there's a certain like fundamental principles about the state-based formalism is that they have this input transition, they have external transitions and internal transitions. Okay, internal transition meaning that some things, okay, were happening. Something that's happening inside of this module, inside this part, okay, which will automatically triggered and change the value of the state variables will become the internal transitions. Okay, if the certain transitions will cause the outside state variable to change, okay, then it become a output transition. Then the other way is that if there's something trigger from outside, okay, which will change these state variables in this area, then become the input transitions. Okay, so actually these input events, output events, and internal transitions comes from the state-based formalisms. Okay, so this is something you need to bear in mind. Okay, then yeah.
So this one, if we go back just now, so the generator, for example, is random arrival. When the let's say the number comes out, we the event's happening, or we change the state first. I think because the state is a snapshot of what is happening, right? It's called so-called event.
Yes.
Because once the event is happening, it's immutable. You cannot reverse
Yeah.
back because it's already happening. So we change the state after that.
Yeah.
Okay, so it's arrived. We call it the state is arrived. Okay.
No.
The state.
Okay. I think that part later.
Okay, everything's
Okay, yeah. Because I think they might not be a right sequence because if it's a normal on-site training, probably what I plan is I will talk about event-based modeling first. After that, I'll talk about this tree formalism.
Okay.
Here, because I know you have certain background, so I'll talk about this tree formalism together here. But I think to have a deeper understanding, probably later we need to go back to the event-based. Okay, so
Next. Yes.
yeah, I think probably we need to go back to the just to focus on the event base first. Then later we can come back here. What is the pointer? Okay, so okay. Hey, what is this? Suzanne, can I help? What happened?
Huh?
I heard some voice. Okay, so now I think just now you may have some doubts about the other formalism. So let's forget about that. Okay, let's forget about that. So just now now let's come back to the event-based formalism to see that this. Maybe just close the.
Yeah, just exit the
browser. Okay, so now let's think about the one situation which we call it GG1 or MM1Q. Okay, so what does this mean? Consider you are going to a post office, okay, or McDonald's. Okay, so post office you want to post a mail, and if you go to McDonald's you want to buy a burger, okay, for example. Consider there's only one counter, okay, only one service, okay, in the office, in the post office or in the restaurant. And in front of this counter, there's only one queue, one line, okay? Then it might have many customers already there waiting to be served, okay? Then you should join the queue, which actually a first come first serve, okay? So you need to wait in the queue until you reach the end of the queue. Then you can be served, okay, by the counter, and serve for some times. When you get your job done, you can actually depart from the system. Then the system boundary is there. Then it's over. Okay. So let's consider this kind of the case. These are scenarios, and we want to simulate, okay, such kind of a system. We want to simulate this is a single server, single queue, post office or the restaurant. Then what should we do? Okay, so this is actually the simplest of problems. Okay, we want to consider and want to practice what is this event-based modeling approach. So, in order to do so,
you just use the arrow. Space. Space.
sorry. Okay, then we described here. We have arrival, which is actually outside the system we consider. Then we have this buffer, which is a queue. Then we have a server. After server, actually can depart. Okay. So let's go back to yesterday's. Okay, when we want to describe such kind of systems. So now I think we don't want to repeat to say what are the components. I think this is already clear. But now I want to ask a question: is what are the state variables? Okay. If you want to take a snapshot of this one for this system, so what are the state variables you want to define? Okay, to describe the state of these things.
Number of passengers in queue.
Number of passengers in the queue. Yes.
Number served by the
Number of server, or maybe whether if it's a single capacity, then whether the server is busy or idle.
Yeah.
Okay.
And number completed also.
Right. Okay.
Number of
number of completed. Okay. Yeah. And
So
also
that-
number of arrivals. If you want to
So
have.
that is the state.
Yeah, this is the state. This is the state. Okay, so these are the state variables. Okay, and just want to mention something else is that if you want to use a continuous perspective to look into this system, then probably you can record the positions of every customers. Okay, whether it's 1 meter from the door or 1.2 meter from the door. Yeah, this is the something you can model. But here is just we don't want to care about that. Okay, so we just consider the number. Whenever it's arrived, a number increase by 1. Whenever it's leave, then the number decrease by 1. So it becomes a discretized. The state variable change can become discretized. Okay, so yeah, so here actually we can simplify this a little bit, that we do not want to record the history, like how many in total have arrived or how many in total have finished. Okay, so we just want to look into maybe a stationary case. Yeah, we don't want, we want the system to be kind of the memoryless. Whenever the customer arrive or depart, we want to forget about them. So in that case, we can actually use this two state variables. One is called the queue, which is used to describe the number of jobs in the buffer, meaning the number of customers in the queue, and we use m, okay, to describe whether the system is idle or busy, okay, for the server, okay. So these are the only two state variables we define here, okay, for these simple systems. Okay, so now you know what does this state variable means. Okay. Then there's another things which we want to describe to define these systems. Okay. So let's ask this a question is, now if you say that this is a kind of the systems we're describing, we're analyzing. Okay, we're analyzing. Okay, a kind of system meaning that for all the system we identify, we analyze here, we actually have a single queue, we have a single capacity server. Okay, so this is for all the systems we're interested now. Okay, but there can be multiple systems, can be many systems which actually follow the same patterns. Okay, we just said. Okay, I mean there can be many systems of this kind. Okay, then how do we differentiate one system from another, which all falls into this kind? How do we differentiate them? Or maybe you ask this a question is, in which case we can see that the two systems actually have the same behavior, are the same. Okay. So what are the parameters we need to check in order to say that there's a two systems are the same or they are different? Okay.
First will be the variables have to be same.
Which variable?
State variables have to be same.
State variable need to be the same. Even for a single system, the state variable.
No. If we have two systems,
Yes.
and we want to check if two systems are same,
Yes.
then initially their state variables have to be same.
You mean initial state variable, initial value of the state variable?
Not the value.
Ah.
The variables should
Okay.
be
This
same.
already said. I said that this is a kind of the system we are interested.
Okay.
Meaning that they have a single queue, single capacity server. So these are all kind of the systems we are interested. But now is that it can be many systems. Okay, it can be McDonald's, it can be a post office, it can be a popular McDonald's, it can also be a McDonald's at a very far place as well. Seldom have people to visit. So yeah, I mean for different kind of the system, how can we say that two systems are the same or the two systems are different?
Because the event.
Yeah,
The
because
same
of the
event.
event.
They all have the same event.
Yeah.
They all have same behaviors. They all have I should say the similar behavior. I mean, they all have the same type of events, have the same type of the state. Yeah. But
If the arrival distribution is same, and if the service distribution is same,
yeah,
then we can say both are same.
yeah, right. So for this kind of system, if the arrival are the same, okay, or if the service pattern are the same, okay, then we can see that the two systems are the same. Okay, so the arrival and the service pattern is actually described or defined by what? Define the distribution of the interval time or distribution of the service time. So these are actually some technical issues. But basically what we want to make sure is they arrive in the same way. If the two systems, if they arrive in the same way, if they get served in the same way, then these two systems are the same. Okay, so yeah, so this is actually called a so-called definition or configuration of the system. When we have this system, then we say that the configuration actually have these two properties we need to set. The first one is interval time, the other one is the service time. Okay.
Sir, one question.
Yes.
As you said, one will be like McDonald's at a crowded place, popular McDonald's.
Yes.
Another is people seldom visit that
Yeah.
place. So how would the distribution be same?
Then in that case, these are two different systems, right?
Okay.
In that case, these two are different. Why they are different? Because arrival are different.
Okay.
One have a shorter interval time, the other have a longer interval time.
Okay.
Even
Yeah.
is the
Even it's the same, I mean same configuration,
Yeah.
same configuration inside the single queue, single server,
Time spent-
even the service, the same server, same kind of the server. Okay. And the other case is that the two McDonald's at the same place, the arrival can be the same, but the service rate can be different. Yeah, one is the experience, they have a faster service, the other have a slower service. Then in that case, the server service time will be different.
Yeah.
Okay.
So to make it like the same system, one of them probably must increase, for example, the service or the
Still, it's not the same. It's
Still not
not.
the
It's not it's not the same system, but the performance can be the same. You are talking about the performance.
Performance.
Yeah, I'm talking about configuration of the system.
Configuration.
We need to make sure that.
overall.
Yeah. So these are the service time and the interval time is actually the configuration. Okay, it's about the configuration. So here is actually what we call the configuration or definition of the system. Yeah. And also in the ODS we refer this as the static properties. Okay, meaning that these are some things not changing while simulation is running.
Right.
I'm not saying that the inter-arrival time is not changing, but I'm saying the distribution of the interval time is not changing. Okay, but if it changed, then we need to abstract another higher level variable to define it. Okay, so these are some things we need to bear in mind. And in comparison, the state variables, we call this as the dynamic properties because they change from time to time while a single system is running. Okay, so let's go to this one. The Q and M are the dynamic properties, the state variables, and the TA and the TS, one is arrival time, interval time, the other one is the service time. It's actually the static properties, which we use this one to define a system. So now just bear this in mind. Okay, then the next questions we want to ask is, now we identify the state variables, okay, for these systems. Now the next question is, what happened? What are the things that it happens if we change the state variables, change the value of state variables? Or more explicitly, what are the events here? What are the events?
Arrive, load, unload.
Arrive, yeah. Arrive, load, and unload. Okay, and actually, some last time some students also talk about like in queue, DQ. It can also be events. Okay, can also be events. Okay, so can I use this one?
Yes, but I think the marker is.
It's okay. It's okay.
Yeah.
Maybe I just do a quick. No. I think probably I just do some quick introduction here. I think probably all you can understand is.
Yeah, this one.
This one. And then probably I just say something more about this one. Is okay. So just remember these things. When event happens, event actually do two things. Okay, each event will do two things. One thing is to update the decision variables. Okay, no, sorry. One thing is to update the state variables. Okay. The second thing is the event, one event when it happens, it will trigger another events, either at the current time or in the future. Okay, so this is about the events. Okay,
So now the T is time, right?
T is the time. So here T is actually a distribution of the time.
Distribution
Of the time. Yeah. So, or random variable, we call it a random variable. It's a random variable. So each time the realization can be different.
Okay.
Okay. So let's just follow this idea to see that what happens when a right event happens. When a right event happens, it actually do these things. It will increase the Q by 1. Okay. So how we update the state variable is a Q equals to Q plus 1. Okay. Then the next thing is it will check whether the machine is idle. If the machine is idle, it will schedule an event to start service, to load this customer or this product. Okay, so this is one. It's idle, it will start serve. Okay, then another triggering is to say that it will trigger the next arrivals after this interval time, TA, okay, which is random variables. Okay, so this is the next thing it will do. So this is about the arrive event. Then the next one is about the load. When load, meaning that the customer start to be served. Okay, start to be served. So when it start to be served, it's going to do the updating. The first one is a Q equals to Q minus 1. Okay, it will reduce the length of Q by 1. The second one is I will let the machine to become busy. Okay, because the server, the customer is loaded. Okay, the M become busy. Then the third one will schedule an events, okay, in the future time, which will call the unload, meaning that it's end of the service. Okay, end the service. Have a time span, have a delay, which is the TS, is the service time. After the service time, then it's got unloaded. Okay, so this is about the load events. How about unload? It will do this, will update the machine to be idle, and it will check if there's still something waiting in the queue. Okay, it will trigger another load event. Okay, to grab this customer and put into a server. Okay, so this is the last one.
So this one meaning the M, the service will check the queue.
Yes.
Okay.
Yes. So this is how we describe. Okay, so this one is actually how we describe the transitions. Okay, of a system, or maybe we can call this internal transitions of systems. Okay, so something like this, you must define the dynamic properties, the state variables first. Okay, before you can say some things to see how the transition is about. Okay, the second one is when you describe the transitions. Okay, you may refer to another transitions. Okay, then when you say another transitions, you also need to specify the time relationship among these two. Okay, so these are some things we need to bear in mind. Actually, all the ways to the time that we start to do the informal description. Okay, so actually I should say that this is the kind of informal description. If you just ignore the state variables defined here, if you replace this one as some English, as some words, okay, then this one is actually an informal description. Okay, so what are the formal description? Later I will show you the event relationship diagram. Okay.
Just one question. If you want to make it a bit detailed, like for example, like sometimes in the object-oriented there, arrive, loading, loaded. Sometimes they have two events, right?
Yes.
So how do we describe? Let's say if we want to make it detailed within the event name. Let's say we have two for arrive is arriving and arrive.
Okay.
Can we say that arrive is actually starting to schedule an event, or arriving is schedule an event?
I should say that arriving itself is not the event. Arriving is not
the event is arrive, right?
Yeah. So actually, I think follow my previous practice, I use the verb.
Use the verb.
I just use the verb to describe the.
So
event.
the event action event only is something like that. Only use the verb.
I only use the verb. Okay,
Okay,
so
because the one that I described is action event. Arriving, arrive, loading, loaded, unloading, unloaded. That's all an action event. So they were, because sometimes I confuse with that. Or maybe, yeah.
I think okay, I either use the verb or the past tense of the verb. Okay, so
So in between we cannot use or the system cannot use that.
I think here is some things we need to understand because I think we need to have a better review of the English is which how do we describe this in a more precise way. But what I did is I either use the verb like arrive or maybe start service. I use start. Okay, start service or end service as an event because I think this is ambiguous to say it this way. But sometimes I use the past tense of the verb. For example, like when we have this lifting process, then I say the lifted. Okay, lifted will become an event.
Then what happened is before lifting, before in between lifting and lifted.
Then there's
cancel.
no event. It's not an event.
It's not an event.
The event can be start lifting or end lifting. I mean, a more precise way probably can be start lifting or end lifting.
Because sometimes in the object lesson, when you say it's loading, before loaded, you can cancel.
No. Here we cannot operate on activities.
Yeah.
We can only operate
Because
on events.
we don't care about the activities.
Yeah.
So that we call lifting means that they start to do that of action. When after the action we call maybe use a past lifted means that this action.
I think arriving is also an action, but we no need to know that they are arriving. We just know that they arrive. Yeah.
Arrive,
I think that's the point. Yeah.
Correct. Upon arrive to trigger action.
Yeah.
Trigger the next action.
So that's why it's in the system in Autodesk it's in the past tense.
Let's say in this way, if you say some verb, okay, you do not perceive as a duration. Okay, for example, arrive. I mean, naturally we think as a single time point. Arrive. Okay,
So
then we just use the verb. Yeah, no, past tense. We just use the verb. Present tense. Yeah, we just use the present tense.
Yeah.
Arrive. Okay.
Right.
But if some things you think you may link to the time span, for example, lift. When you say a lift, okay, then you need to be careful. Is that we should use like a start to lift, or start lifting,
or
end
introduce
lifting.
another verb.
Yeah,
Start-
using another verb,
okay.
which we do not have this
Correct.
ambiguities
Makes sense.
about the
Okay, I
time
understand.
span, or maybe lifted. Okay.
Yeah,
In this
because
one-
otherwise I understand what you mean. If we don't do that, we cannot change the state of.
Yeah.
Okay.
We need to be careful is when we
Yeah.
look into the name, it should not be a time span. It should be a time point.
Time point. Yeah.
This one should link to the time point.
Correct.
Yeah, so this is some things
Got it.
we need to pay attention. And also we have some like a standard or maybe like convention. For example, usually we have this attempt to do something.
Yeah.
Attempt to start. Okay, or maybe you have a request to start.
So prepare or request.
Yeah. So these are actually some like special terms we can use. Okay, in our modeling.
Yeah.
Okay, so yeah, so just continue to say that. Okay, so here is actually some things we want to practice
Why is automatic running?
because it's simulation.
Oh, it's
Okay,
I
so
think it's better explain one by one.
yeah, so this is actually a menu.
One by one. Yeah.
Still automatic.
Oh, yes.
Later I
Okay.
need to change the animation a little bit.
Yeah.
Okay. So here is actually some things we can practice by ourselves. Okay. So every time I give this to students, I let them to do in this way. Is to get a piece of paper. Okay. Then
But
just
okay. Something wrong with the PowerPoint.
it's not because of my animation.
No.
Routine, we just showed to you in the previous slides. Okay. Then this is the initial things I give to you. Okay. Then you are actually expected to carry out the simulation on a piece of paper. Okay.
Yeah.
How do you do it? Okay. The first, This is state variable, right? This Q and M state variable. These are the initial value. Then I tell you that there's actually one event in this so-called future event list, which are stamped at a time 3.
3.
Time 3. So every event here is time stamped. Okay, so stamped at a time 3. Then how do we want to proceed? We need to execute the event. So which event we should execute? Of course, arrive.
Alright.
Because only one event here. But what happens if there are multiple events in the future event list? So we just look into a timestamp, we find the earliest one to execute. Okay, so this is the protocol. Okay, so when we execute the arrive, what will arrive do? It will increase the queue by 1, right?
Yeah.
It will okay. The first thing I do is I find out, I retrieve the event to say, this is the event I'm going to execute. Okay, from this list, I retrieve the first one. Okay, then I will say that what it do is will increase the queue by 1. That's all right. That's what we update the state variables. Okay, so we can see that it's update this one and this one no change, M no change. Okay, then how about the triggering of the events? It will trigger 2 things. The first one is if the M is idle, then it will trigger a load event. Okay.
Okay, I have a small question. Why the arrive when we stamp 3 is considered as a future event list? The event is not happened yet, right? How come it's already in the list?
This initial future event list must have something.
We must,
We must have
we
something.
assign.
We assign. I mean initialized.
Okay.
Why is, I mean the first row is initialized, the constructor. It's what the
Okay,
constructor
it's a
is doing.
constructor, yeah.
Yeah, it's a constructor. is
We,
doing.
we intentionally added in the future
Yeah,
event
yeah,
list.
yeah. Otherwise, the
Okay.
simulation cannot start
Cannot
if
start,
there's
yeah.
nothing's inside. Okay, it must
Okay.
have an initial event.
Now I understand.
Okay. Then for this one, the event they're going to schedule is one load events at what time and now. What is now is 3. Okay. Then the second one is it actually schedule another arrive after the TA. Okay, so the TA, the first TA is a 3. So you need to schedule arrive at the 6 and also schedule a load event at 3.
Yeah.
Okay. So this is what will happen. Okay. Why is 3? Sorry, 3 is here. So what you have is 2. Okay, so 3 plus 2 equals 5.
Yeah, what I understand is why the load 3 not in the retrieve event.
No, next week will go.
This is the first, now we are retrieving this one. Because of the first row, we retrieve this one to execute. Then this is resulted.
This is initial event.
This is the resulted. This is the resulted future event.
Okay, so the input is directly to the future event list of the event. Starting point, this load.
This is the starting list. This is the starting list.
And then
we retrieve this one here. Okay. Then this is 2 events triggered by here.
No, I know. Load 3 is I understand. Arrive 5. Where it came from?
The trigger by arrive.
Trigger by arrive and then to call 2 events.
Remember here, arrive do 2 things. Schedule event load, schedule event arrive.
So looking at another
It's a
type.
trigger by arrive.
Oh, okay.
Okay.
So arrive 5 is not a new event.
It's a new event. It's a new event. Triggered
yeah.
by arrive 3.
Trigger once I arrive first event upon arrival, and then they go to check against the queue and also to check against the server, and then find that once arrival, once initially I put it into the queue, so the queue increase 1, and then at the same time to call another arrival event again.
Just follow this one. Just follow this table.
Yeah, okay.
Precisely follow this table. Yeah. So if the M is equals to idle, then you will do this event. Okay. At the time now, what is now is 3. Okay. Then no matter how, it will schedule another event of arrive. Actually, it's itself, but at a different time.
So the generator goes to the future event list.
Yeah, yeah. Then the generator will put into future event list.
That's my question.
Okay.
I thought it's the retrieve event.
No.
Okay.
I mean, it's a future event list. When the arrive event already retrieved, then we remove from the future event list. Then when I execute it, it's a generate 2. One is a load, another is arrive.
I think you understand if the future event list put on the first column. Easier to understand. No, the column, the future event is on the left side.
Maybe
not on the right,
we
yeah.
can put some animation.
Yeah.
This one will be.
So future event list, retrieve event, then the state. I think it's more easier to understand because
call for the event.
yeah, because the generator comes to the future event list. Yeah.
Okay, I think I
Okay,
should.
I got it.
I think I should.
Yeah,
I should
you can have to
pause
go to
this
meeting
now.
first.
Someone want to continue? Have to continue this?
I can continue.
Yeah, maybe
yeah,
Ranajan
yeah.
can continue
Yeah.
this one, then probably can finish, then we can wait for tomorrow. Lah.
Yeah, sure.
Okay, so I need to rush
Yeah,
to
okay.
the meeting. Yes.
Okay.
Okay.
So basically, like I will say, we will have one more column, simulation time. So at the at 0 simulation when it
Alright,
started,
yeah, we
it will,
need to have.
the initial event is it will generate a arrival. So the first arrival happens at 3 minutes. So here the simulation time is, let us assume one more column.
Yeah.
It's 3. 3 at simulation time 3 there is a arrival.
Yeah.
Right?
Correct.
Arrival will trigger will increase the queue.
Yeah,
So-
I think I suggest we better put the FEL column on the left instead of the right.
Yeah.
Yeah, it's easier to understand.
Yeah, yeah.
In my point of view, correct or not? Because this one is. Where does it came from? Suddenly it's pop up in here. But if here we put in here and the simulation time
Yeah,
before
yeah.
that, then we know it's arrived and then we treat the event
Yeah.
and then goes starting the process.
Yeah.
Oh, now I understand. How come suddenly pop up in here? It's like someone throw, wow, you arrive. Yeah. Now okay.
So
Now I
the
understand.
thing is here also second row also simulation time is only 3, and at the same time it will increase the queue and it will check if whether server is free.
Yeah.
Server is free,
correct.
so it will schedule load 3.
Yeah.
Right?
Load is because there is an arrive at 3.
Yeah,
That's
so-
I understand.
Yeah,
So
it
I
immediately
understand.
go to, at simulation time 3 it will go to load because already server is free.
Yeah.
So
And then generator comes in.
then at the simulation time it is also
Yeah.
generate the next arrival,
Alright.
which is in 2 minutes. That means arrival will happen at simulation time 5, right? So this is also simulation 3, time 3. So load is retrieved, so that means when load is processed, the server will become busy and queue will become 0. And it will retrieve list will now only have only arrival 5 and unload 6, because like server is now having arrival 1 and the service time is something like 3, I think.
Yeah, this one is
Service
depend,
time
right?
is 3.
Sorry, this one is depend. If the arrive is 7, it will be on the right side, right? Because this one
Yeah,
is
yeah,
right,
yeah,
right?
yeah.
That's okay.
So basically like you see these two
Like
sets,
in
this
multiprocessor.
Yeah, this one is actually similar like queuing the
Yeah,
processing of
yeah.
yeah.
So basically this is the arrival times and this is the service times. So the first arrival will take service time 3.
Ah.
So the schedule unload is 6, 3 plus 6.
Yeah.
Because the current simulation time is 3.
Yeah.
So now this will, there are 2 events, future events. The first event in the list is 5.
Yeah.
The simulation will move to simulation time 5 and the next arrival will happen. So similarly it will follow.
How would 6 come?
6, see, we have loaded one arrival, right? There is one arrival. So the server has taken it at server simulation time 3, right? Now simulation time is 3 and I will take, first service time is 3 minutes. So I will unload, I will complete that load at 6, right? Simulation time 6.
That's
So
why
that
you
is
see
my
on
unload
3
is-
plus 3.
5 or 6, which is fast, they will come.
Yeah.
Yeah, that's why you see in the O2 desk there is a sorted list. So a sorted list is actually for the event list, future event list. So everything that you put in there automatically will sorted by the
By time.
simulation time. Yeah.
It's like scheduling unloading at simulation time 6.
Yeah.
Because service time is 3 and the current simulation clock is 3. So it's 6. Right? Now at simulation 5 it came, so it added queue increased there at 1 and server is busy. So this is removed from the future event list because it's already happened. So unload 6 and this queue at 5 we are generating next arrival.
5 plus 4.
Yeah, similarly like that. Yeah, now you understand this, and if you have any doubts, like we can clarify.
Yeah. Yeah, I think it's better we add the, like you said, the
Simulation.
column simulation time, timestamp.
Usually that happens.
Yeah, and the future event is put on the left side, so
Yeah.
easier to, yeah. Because we actually, we can also add another column called it generator. So when the generator comes, but we will add more row
Yeah,
to explain.
but actually it's a like you are adding an event which will generate.
Yeah,
It will generate
the generator
So
is
we are saying-
because generator is a random,
Yeah.
and the time is also random.
This
Yeah.
this one is going to let TA and TS. These two equation become a kind of a diversification.
Yeah,
because
these two.
Yeah, I mean for beginner like me, instead of this, it's better put in here so we know which one the time comes 3, 5.
Yeah,
6,
simulation clock.
So it's simulation clock. Yeah, it's easier for us to understand.
There is no load 8, only unload 8.
Unload.
So unload happens at 6, right? So this is
No,
like
this one-
simulation clock 6.
Yeah.
So it's unloading. So it will
For-
become
No,
idle.
she's asking